Okay, so in the last video we took a look at velocity-dependent forces and examined the linear case. Now we're going to go ahead and take a look at the quadratic case. And I'll warn you right now, this is definitely a little uglier. We'll start by taking a look at the case for downward motion. Again, here, remember with the quadratic case, because the v is squared, we have to handle the directions by hand. So here's our object. It's going down, velocity v. Two forces acting on it will have gravity down, and we'll have our air resistance force acting up. Now, here, for computational convenience, I'm going to choose down to be positive. So when we write Newton's second law, we'll have that mg is positive, pointing down. Now here, I have to choose between plus or minus c2v squared. Since v squared will always be positive, I need the minus sign in order for it to point up. So minus c2v squared, and that will equal ma, so m dv dt, looking ahead to trying to do some integrals. Okay, we can cancel the m's if I divide that through by m, and I can rewrite that so I can pull a g out. 1 minus c2 over mg v squared equals dv dt. Okay, we'll call that double star. So let's go ahead and find our terminal velocity. Now before, we just went ahead and solved for it and then let t go to infinity and see where that got us. This time we need, if we can be clever, that would be better. And so we'll try to be a little bit clever. We can recognize that once we reach terminal velocity, sort of by definition, the acceleration is going to end up being 0. So we can go ahead and find our terminal velocity directly, and that will probably be a little happier for us. So we'll put in v terminal here, 0 there. So we will get g times 1 minus c2 over mg v terminal squared equals 0. And we can rearrange and get that vt equals the square root of mg over c2. All right. So at least we found our terminal velocity without having to do a whole lot of horrendous math. Now, when we get to it later, sorry, there, that looks really bad right there. That should be a dt. There. Now, when we get to it later, we can use this to check our work, because now we're going to go ahead and try to solve it for real. So let's rearrange it. At the very least now, because we've got this expression for v terminal, we can go and take a look back at our equation of motion and realize that this becomes v squared over v terminal squared. So we'll write it like that. Alright, so dv dt equals g times 1 minus v squared over v terminal squared. Okay, so we can go back to the same well we usually do. We can separate our variables. dt equals dv over all that stuff, I'm afraid. 1 minus v squared over vt squared. Well, we can make it look a little prettier. Vt squared over g times dv over vt squared minus v squared. Okay, now going from here, we integrate both sides, so we'll let this be t minus t naught. And now here I'm not assuming we're starting at t equals 0 because we may need to join boundary conditions, so I want to be a little more generic in case that we have to transition from moving up to moving down. And I'll just say the easiest way to do this integral, frankly, is just to look it up. And when you do, you get Vt over g equals the inverse arctangent of V over Vt minus the inverse, minus the arctangent of V naught over Vt. Woohoo. Okay, just a quick aside for those of you who might not be completely up on your hyperbolic sines, cosines, tangents, those kind of things. This is when mathematicians extend trigonometry from circles to hyperbole. We wind up creating sinh, cosh, and tanh is usually how you say them. Sinh of theta is defined to be e to the theta minus e to the minus theta over 2. So this is like the definition of sine using the Euler identity, but without the i's. Similarly, cosh of theta is e to the theta plus e to the minus theta over 2. And then finally, tanh theta, you can show is e to the theta minus e to the minus theta over e to the theta plus e to the minus theta. Okay, that's all we need from that right now. There's no need to get into tons of hyperbolic trigonometry. So anyway, we can take this monstrosity here and we want to pull v out from it. So we'll get that by saying that v equals v terminal times the tanh of t minus t naught over tau minus the arctangent of v naught over v terminal. Woohoo. Oops, sorry, I skipped a step there. I skipped a lot of steps, my bad. Let me remember this because we'll get to it later, but let me motivate just a little more of it than I did just there. Okay, I'm sorry, let's go back to actually trying to solve and crap. So we had that horrendousness there. And the first trick was to say that the characteristic time, like before, we'll say, whoops, characteristic time is Vt over g. So then we can get t minus t naught equals characteristic time times the arctangent of v over vt minus the arctangent of v naught over vt. And then from there you go ahead and do your trigonometric manipulations to get what I had promised you earlier. Okay. So that's as clean as we can make it, unfortunately. That is our velocity as a function of time. And to get the position, yeah, you have to integrate it. Now, because that's getting a little ugly, we can look at some simpler cases, like we can look at the case of us dropping the object. So let's let the initial velocity be 0 at an initial time of 0. So if we do that, that makes all my t naughts go away. That makes this the arctange of 0, which is conveniently equal to 1. Or I'm sorry, is conveniently equal to 0. So we get that v equals v terminal times the tangent. The tangent of t over tau. So that's at least a little nicer. We can write that also as v terminal times e to the t over tau minus e to the minus t over tau over e to the t over tau plus e to the minus t over tau. And if you multiply numerator and denominator by e to the t over tau, you can make this look a little prettier and get that v equals v terminal times e to the 2t over tau minus 1 over e to the 2t over tau plus 1. I guess it's a matter of aesthetics, which you think is cleaner, but at least this we can think about a little better. Now, for this limiting case, we can then go ahead and pretty readily get the position. We can go ahead and integrate this, and again, just go ahead and either use Mathematica or look up the integral. You will get that y equals vt tau times the natural log of the cosh of t over tau. And again, that's for these initial conditions. All right, so now if you go and take a look in your text, remember example 2.4.2, which was horizontal motion. We're going to go ahead and revisit this. So this is horizontal motion. So we have our only force will be minus c2v squared equals m dv dt. And this we can solve a little cleaner. So we can pull the dt to the one side just like before, get minus m over c2 dv over v squared. Okay, we'll integrate that from, we'll do 0 to t, because we're not really worried about joining solutions here, and integrate from v naught to v. Okay, so left side gives us t equals, right side is going to give us m over c2 times 1 minus v minus 1 over v minus 1 over v naught. All right, now as usual, you want to go ahead and rearrange this to get v as a function of t, because ultimately we're going to try to express x as a function of time. So let's go ahead and do that. When you rearrange it around, you will get, so I'm just skipping some tedious algebra here, v naught over 1 plus c2 v naught over m times t. All right. Now, that's getting to be a little annoying to write. So let's take this bit right here and we'll call that k, just to make this a little easier to write. So then this will equal v naught over 1 plus our k t. Okay. All right, so then we can go ahead and play the same kind of game as before. V, we can say, hey, v is dx dt, right? So then we can say dx equals v naught over 1 plus kt dt, integrate from 0 to x. Well, you can assume that we start at x equals 0, then integrate here from 0 to t. Again, you could just go ahead and stick this into a Mathematica or something like that. But again, let's just refresh our memory of doing u substitutions. So we can let u equal 1 plus kt. So du equals k dt. So that means dt is equal to du over k. And we put that in there. So this becomes, we can pull out a v naught from here. It's a constant. We'll get a k over there from doing the u substitution. Then we'll have the integral du over u. Again, we have to be careful about our limits. Our limits are going to run from t equals 0. That becomes u equals 1 to t equals t. So that's 1 plus kt. So this will equal v naught over k times the natural log of 1 plus kt over 1. Okay. So we get a final answer of x equals v naught over k times the natural log of 1 plus kt. And you should always, always, always ask yourself if the answer is reasonable. And here we have a problem with this answer. The problem is that if we let t go to infinity, v approaches 0 like we would expect, but now let's look at this x here. We will be taking the natural log of infinity, which is still infinity. So that means that the position is going to infinity. So according to this, you're asymptotically approaching a speed of 0, but you'll never you'll always keep moving. Now, I don't know about you, but I haven't seen that happen too much in the real world. So what's the error that we did here? I would encourage you to pause the video, think about it, and then when you come back, I'll give you the answer. Okay, so the issue here is that we over-approximated. And this is a real danger that you have to watch out for. So this is an example of over-approximation. The problem here is that as v approaches 0, we're going to get to a point somewhere. C1v will become a bigger deal than C2v squared. And I'll put absolute values in there if you must. But the deal here is that at some point, the linear term, which we neglected because, frankly, it gets really hard to deal with both linear and quadratic at the same time. At some point, the linear term dominated. And so and then if we remember what the behavior was for linear drag, we know that it did indeed come to a definite halt. So this is the danger of pushing approximations too far. You have to keep in mind what your assumptions are. Okay, so that concludes this video. In the next video, we'll go ahead and do a quick treatment of analyzing this with numeric methods.